No one had ever seen it. No one could touch it. No one even knew if it really existed. Yet, this invisible particle was passing through your body, through the Earth, through entire planets, billions of times every second, without leaving a trace. Today, we call it the neutrino. But for more than 20 years, it was nothing more than a desperate idea, invented to save physics from collapsing. And the story of how neutrinos were discovered is not a story of advanced machines at first. It is a story of confusion, broken laws, and one physicist who quietly wrote a letter that would change science forever. Let's go back to the early 20th century, a time when physics seemed almost complete. Atoms had been discovered, electrons were known, radioactivity was being studied, and scientists believed they were close to understanding everything about matter. But then, something went terribly wrong. Physicists were studying a process called beta decay. Certain radioactive atoms, like uranium or radium, spontaneously transformed into other atoms, and when they did, they emitted electrons at high speed. This process was well known, and according to the laws of physics, especially the law of conservation of energy, the energy before and after the decay had to be exactly the same. Energy could not simply disappear. So scientists measured the energy of the emitted electrons, expecting to see fixed values, just like bullets fired from a gun with the same force. But that's not what they saw. Instead, the electrons came out with a wide range of energies, sometimes high, sometimes low, sometimes anywhere in between. It was as if energy was vanishing, or worse, as if the most fundamental law of physics was being violated. This was not a small problem. If energy conservation failed, then physics itself was broken. Some scientists even suggested something unthinkable, that maybe energy conservation was not always true at the atomic level. But one man refused to accept that idea. His name was Wolfgang Pauli. Pauli was already famous, known for the Pauli exclusion principle, a rule that explains why matter does not collapse and why atoms have structure. He was brilliant, but also deeply cautious. And in 1930, while attending a conference, Pauli became convinced that the missing energy in beta decay had to be carried away by something else. Something invisible. Something neutral. Something incredibly hard to detect. So Pauli made a bold move. Instead of publishing a formal paper, he wrote a letter. A letter addressed to his fellow physicists, which famously began with the words, "Dear radioactive ladies and gentlemen." In that letter, Pauli proposed the existence of a new particle. It had no electric charge, almost no mass, and interacted so weakly with matter that it had never been seen before. This particle would escape the experiment unnoticed, carrying away the missing energy and restoring the law of energy conservation. Pauli himself was not confident. He even apologized in the letter, saying that he had done a terrible thing by proposing a particle that could not be detected. At that time, suggesting an undetectable particle was almost heresy. Physics was supposed to be testable, but Pauli believed the alternative was even worse. And so, the neutrino was born, at least in theory. A few years later, another physicist stepped in and gave Pauli's idea a solid mathematical foundation. His name was Enrico Fermi. Fermi was one of the greatest physicists of all time. And in 1934, he developed a complete theory of beta decay. He included Pauli's mysterious particle, refined its properties, and gave it a name, neutrino, meaning little neutral one in Italian. According to Fermi's theory, when a neutron decays, it turns into a proton, emits an electron, and emits a neutrino. The energy is shared between the electron and the neutrino, which explains why electrons appear with different energies. The theory worked beautifully. There was only one problem. No one had ever detected a neutrino, and detecting it seemed nearly impossible. Neutrinos have no electric charge, almost no mass, and they rarely interact with matter. A neutrino could pass through a wall of lead, through the Earth, through your entire body, as if nothing was there. Trillions of neutrinos from the sun are passing through you right now, and you don't feel a thing. For many years, physicists believed neutrinos were real, but untouchable. Some even called them the ghost particles of the universe. Then came the 1950s, and with it, a new kind of experiment. Nuclear reactors. Nuclear reactors produce enormous numbers of neutrinos. When uranium nuclei split inside a reactor, they undergo beta decay, releasing a flood of neutrinos. If neutrinos could be detected anywhere, it would be near a reactor. Two physicists decided to try: Frederick Reines and Clyde Cowan. They were fully aware of how crazy their idea sounded. They were trying to detect a particle that could pass through Earth itself. But they also knew that with enough neutrinos and a clever enough detector, one interaction might finally be seen. They designed an experiment based on a rare process. Very rarely, a neutrino can collide with a proton, producing a neutron and a positron. The positron would quickly annihilate with an electron, producing a flash of light. The neutron would be captured shortly afterward, producing another flash. Two flashes, separated by a tiny delay. This double signal would be the signature of a neutrino. Reines and Cowan built their detector near the Savannah River nuclear reactor in the United States. They used large tanks of water loaded with chemicals that produced light when radiation passed through. Day after day, they waited. Most neutrinos passed through without interacting, but occasionally, very occasionally, the detector flashed, then flashed again, exactly as predicted. After years of work, careful analysis, and eliminating every possible alternative explanation, Reines and Cowan announced their result in 1956. They had detected the neutrino. The ghost had left a footprint. When Wolfgang Pauli heard the news, he was overwhelmed. He sent a message congratulating the team, relieved that his desperate idea had finally been proven real. Physics had been saved. But the story did not end there. In fact, this was only the beginning. As experiments improved, physicists discovered that neutrinos come in different types. First, the electron neutrino, associated with electrons. Then, the muon neutrino, discovered when studying cosmic rays. Later, the tau neutrino, completing the trio. Each one was strange, elusive, and difficult to study. Then came another shocking discovery. For decades, neutrinos were assumed to be massless. But in the late 20th century, experiments studying neutrinos from the sun and from the atmosphere found something unexpected. Neutrinos were changing their identity. An electron neutrino could turn into a muon neutrino, then into a tau neutrino, and back again. This phenomenon, called neutrino oscillation, is only possible if neutrinos have mass. This meant that the standard model of particle physics, one of the most successful theories ever created, was incomplete. Once again, neutrinos were breaking the rules. Today, massive detectors are built deep underground, under mountains, or beneath ice in Antarctica, shielded from other particles. These detectors watch silently, waiting for tiny flashes of light, caused by neutrinos arriving from the sun, from exploding stars, from distant galaxies, and even from the earliest moments after the Big Bang. Neutrinos are messengers from places we could never otherwise see. They carry information from the core of stars, from supernovae, from black holes, from the birth of the universe itself. All of this started with a problem, a missing piece of energy, a broken experiment, and one physicist brave enough to say, "What if something invisible is there?" The neutrino was not discovered because it was easy. It was discovered because physics refused to give up on the truth. And even today, as you watch this video, billions of neutrinos are passing through you, silent, invisible, and real.